Okay, so for problem number 2, we're given that suppose that S is inductive, which of the following must be true? So first let's talk about what it means for a set to be inductive. So for a set to be inductive means if the set has the first element, maybe we can call this n, then it means that n, if we look at the analogy of the dominoes, n is going to topple n plus 1, which in turn, if you push it, it's going to topple n plus 2, which in turn is going to topple n plus 3, and so on and so forth. The idea here is that if the first one's true, then that guarantees that the next one's going to be true, which in turn is going to guarantee that the second one after it's going to be true, and so on and so forth. So we can summarize the inductive principle as being if n is true, then n plus 1 is true, right? Or if n belongs to S, then n plus 1 belongs to S. You could say S as being the set for which the statement is true, right? So let's look at these statements here and see which ones make sense. So for item A, we're saying if n plus 1 belongs to S, then n belongs to S. And you can see here that this is the inductive statement, right? And it's actually the converse. Because the converse is if n plus 1 belongs to S, then n belongs to S. And that's not true because the converse is not logically equivalent to the statement itself. Because it could be, for example, we could say that this first one is just n plus 1, right? It's kind of arbitrary what you call n plus 1. So we could say that this is n plus 1 and that's n plus 2 and so on and so forth. So we could begin our set here at n plus 1. It doesn't mean that the element n is going to be there. So that is definitely not true. So that's going to be a no. Now the next one is going to be if n belongs to S, then n plus 2 belongs to S. So let's say that this is n. Well, if n belongs to S, then n plus 1 is going to belong to S, right? And in turn, n plus 1 is going to topple over the next one, which means that n plus 2 is going to belong to S. Because the inductive property is this idea that if you have one element, it's always going to have its successor. So yes, this does have the inductive property. What about if n plus 1 does not belong to S, then n does not belong to S. And you can see that this here is the contrapositive, right? So if n belongs to S, then n plus 1 belongs to S. So that's the statement. So the contrapositive is if n plus 1 does not belong to S. So we begin with a denial of the consequent and then say, then the antecedent must be false. Then n does not belong to S, right? And we know that the contrapositive is logically equivalent to the statement. And that is in fact true because we're saying, hey, if the set S is inductive and this guy here is not there, it must mean that n is not there. Because if n were there, then it would guarantee that n plus 1 would be in that set. Because that's how the inductive property works. So the fact that n plus 1 is not there definitely means that n is not there as well. So that's going to be yes. And for D it says if 6 belongs to S, then 11 belongs to S. And that is true because say that this is 6. Well, if 6 is in the set, then 6 is going to guarantee that 7 is in the set. And 7 is going to guarantee that 8 is in the set, and so on and so forth. So that's eventually going to guarantee that 11 does belong to the set as well. And for item, so that's a yes. And for item E, we have 6 belongs to S and 11 belongs to S. And that's not true because the starting point does not matter. So it could be that we started at, say, 12, right? The idea here is that if 12 is in the set, then it means that 13 has to be in the set, right? It's just the idea of the successor. It doesn't say anything about the starting point. So it could be that the starting point is somewhere beyond 11, right? So this is not necessarily doesn't have really anything to do with it being inductive. So that's no. And that is it for problem number 2.